So once we've done the lithography, we can pass the wafer into what's called a CD-SEM, a critical dimension SEM, and we can verify the dimensions that we've achieved. And if we haven't got what we wanted, we can strip off the resist and pass and repattern using a different exposure dose. So the good thing about that is we don't go away and etch a wafer, and that's obviously a permanent change if the dimensions are wrong. And you'll notice, I just thought I'd give you a little bit of data about CD-SEM. I've sort of exaggerated a cross-section profile you might get of in this case, a waveguide or grating structure. And you can see on the SEM image on the left that you'll see these bright regions at the edge of the features. So that's the sloped area. So we can actually measure the top of the slope and the bottom of the slope by CD-SEM and then estimate the middle point, or the sort of the average width of a device. And here this shows some typical data that we might see in the cornerstone process. This particular process is from the 340 nanometer SOI platform, and the target feature width for a waveguide is 450 nanometers. So you can see a map of what this might look like with some typical sort of tolerances that you'll see. And I'll sort of skip over this, but this is just to show variations you might see across wafers. So the previous slide was on a single wafer. This now shows multiple die on multiple wafers, but in this case it's for a 220 nanometer SOI platform, and it's the grating coupler etch. So we're targeting a slightly different dimension. Right, so once we've done our lithography and validated it, we'll then pass it into another process, in this case etching. So what is etching? In layman's terms, it's removing of parts of the substrate. There are two main types of etching. We can have dry etching, which is done usually with plasma chemistry, or we can use wet chemical etching. Now with dry etching, we can achieve nice straight sidewalls like you might want for a waveguide. With chemical etching, it etches in all directions, so it's what's called isotropic, which obviously doesn't work well for forming waveguides, but it's very good. It can be extremely selective to certain materials, so it's good for things like stripping resist or removing the entirety of certain layers. Now, even within a dry etch process, we can have elements of chemical etching and elements of physical etching. So that the chemical etching will be isotropic, as the diagram on the left shows, so it will cause an undercut and etch in all directions, but the physical etching will be more directional, so it will help us to form sort of rectangular or square structures. And in a dry plasma process, we would have a combination of the both to try to achieve whatever our targets are. I think I'm going to skip over this because I am going to be short on time, but the left hand side shows what a plasma chamber might look like. If you want to watch this back on YouTube, you can pause it and read the text. It explains how a plasma is formed in the chamber. The idea of the plasma is it breaks down the gases that you input, and it forms very reactive neutral elements plus some ions that can be accelerated towards the substrate, and that causes the physical etching. The very reactive neutral elements are what cause the chemical etching. Now the ions are accelerated towards the substrate because when the plasma forms, the very light electrons that are alternating in this electric field that's applied to the chamber to create the plasma, these electrons accumulate on the stage, forming a negative bias that then accelerates the positively charged ions in the plasma towards the substrate and causes an etching here. But it's important to consider that we also etch away the mask, so we need to have a mask layer that's thick enough or a process that's selective enough to what we want to etch, to make sure that we don't run out of resist during the etching process. And this table just sort of summarizes what might etch different things. I picked silicon dioxide and resist since they're very commonly used in silicon photonics. The top 3 lines are all dry etch processes. You'll notice we can use argon, which is an inert gas, so that's pretty much just a physical etching process, so it'll etch anything in its way. Or we can use different gases. Just to point out, oxygen plasma is very selective to photoresist, so we use that to typically strip the resist once we've finished etching. And the bottom 3 rows show different chemicals that are very selective to certain things. So hydrofluoric acid is very commonly used to etch away silicon dioxide. Now, moving on to deposition, we don't always want to remove things. We sometimes wish to add layers. There are 2 key types, low pressure chemical vapor deposition and plasma enhanced chemical vapor deposition. The concept of them both is that we want to input some gases and we want to break down these gases so that they react in the chamber and cause the growth of a film. Now, in the low pressure system, the gases are decomposed by heat, whereas in the plasma system, they're decomposed by a plasma. And this slide compares the 2. Now, a general rule of thumb is that the higher temperature gives you a better quality film. So you might think, why don't we always use the low pressure CVD at a very high temperature to give us the best quality films? But the answer to that question is that that temperature will affect other devices that may already be built into your substrate. So thinking back to the carrier depletion modulator that I talked you through, at the point we come to add the cladding, which is where we'd use a CVD process, we already have lots of dopants in the wafer. If we used a low pressure, high temperature process, all of those dopants would diffuse and you basically just destroy your device. So we need to use a plasma chemistry that can happen at much lower temperatures so that the dopants aren't diffused. The sort of drawback is that we have a lower quality film. And again, so being short on time, the left-hand side shows what a CVD system would look like, and you may think that's almost the same as an etching system, and you'd be right. The key differences are shown on the right-hand side. The main one being that in this case, we actually ground the table. And the reason for that is that prevents an accumulation of bias. So we don't want to accelerate high energy ions and etch away material in this case. So we bias it so it just naturally lets the film grow. And in the case of etching, we'd usually cool the table to prevent the resist burning. But with a deposition process, we'd heat the table to encourage the film growth. And once we've done the deposition or the etch, we then need to characterize the layer thickness in some way. And now within Cornerstone, we like to use ellipsometry to do this. And this video shows how we do that. So this is one of our very talented cleanroom technicians. Just picking up a wafer out of the box. You'll notice he's got his hand under the wafer. That's just good practice, just in case it slips out of the tweezers. We don't want to smash it on the floor. We're now going to align the beam to certain structures on the wafer. So when you send designs to a foundry, what the foundry will always do is add their own test structures to the design. In this case, I don't know if you can see on the computer screen, we're aligning the beam to big boxes that we've opened to be able to measure the etch depth. The beam size coming out of this ellipsometer is quite large, so we need a big open window in the resist so we can characterize, in this case, a layer thickness. So we have recipes set up because often we've got same size cells. So what we're doing now is we're doing a map of the thickness across the wafer. You'll see the stage moving, and when it pauses in between each movement, that's when it's actually gathering the data. And once that's done, we get a map of the layer thicknesses. So what we're looking at here is actually a silicon dioxide layer thickness map across a wafer after a CMP step. Okay, so and once that's all done, we finished our wafer. Clearly, we want to test it. And within Southampton, we have a very nice wafer scale test capability. This video is showing an optical test. If you can just make out a fiber coming in from the left-hand side, I'm not sure if you can see my cursor. This is an optical fiber input and output. This is an automated system that lets us do, hundreds of measurements per day. So we can really get nice data showing different tolerances across the wafer. Okay, so I knew this would happen. I'm going to have to be selective on which case studies I may cover. I think probably this one's quite interesting. So the processes we use, the recipes we define, clearly need to be developed in the first place and then maintained. So the way that we'd often do that is first we do a literature search on what's already known. And then based on our particular tool, we would do a parameter suite of parameters that we consider to be important. And we define a target properties. We go away and etch different wafers under different conditions and then observe the trends. So in this case, we're looking at the sidewall angle of a silicon etch. And what you can see is on the screen, we've got 11 different recipes that we've selected with a variation of RF power on the y-axis and the C4F8 gas flow on the x-axis. And you can see a clear trend here in the sidewall angle of the etch. And the reason for that is that we use C4F8 to create a polymer during the actual etch process that accumulates on the sidewall of your etch region that protects it from undercut. So if we have a high flow of this gas, we build up protection on the sidewall, we actually end up with an angled etch. And I'll show you on the next slide what an SEM image might look like. So it's nice to have this type of data because working in a research environment in a university, the processes do drift a little bit, but it does mean that we can correct them over time because we can follow the trends that we've observed from these data points. And I've just picked out 3 that are shown here, data point 4, 3, and 5, to show you the effect that we have by changing the C4F8 gas flow. So when we have a low C4F8, you can actually see a slight undercut of this profile, this waveguide. And on the right-hand side, where we have a higher flow, you can see we're starting to achieve an angle on the etch. You'll also notice that the etch is actually much slower because we've got a significant more silicon left after a fixed etching time. So we can do this for a number of different parameters, but I don't have time to go through all of them today. I'm going to skip over this next case study and show you this one instead. So this is about high-speed modulators. I've taken a screen grab from a post that EPICSFAB posted. EPICSFAB are a European Silicon Photonics Consortium. This is what they called the 100 Gigaboard Club on pure out-and-out silicon modulator performance. So we are very proud that of the 5 that were selected, Cornerstone actually built 2 of them. But we've since got even better. The latest results that we've achieved, I say we, it's really down to the brilliant design work of other colleagues. Cornerstone built the Silicon Photonics modulator, and they were able to achieve 182 gigabits per second on-off keying using just a silicon depletion modulator. The way this is possible is really through the co-design of the electronics driver chip and the Silicon Photonics modulator itself. And some of the other data is shown on the screen. Notably, there's a very low power consumption per bit from the driver. So this is really pushing the limits of what is possible with silicon technology. And now, briefly, these are 4 slides I borrowed from EPICSFAB, just to show you what the foundry ecosystem across the world looks like. On latest count, and I do apologize if any have been missed, but we counted 30 available foundries focused in the North America, Europe, and Asia. The eagle-eyed amongst you will notice some of the largest foundries in the world are now interested in silicon photonics, namely TSMC, Global Foundries, Intel. Intel have been in silicon photonics for many years. If you zoom into Europe, you'll see that Cornerstone is the only one in the UK. There are other foundries that are focused mostly on research environment, but there are a couple picking out X-Fab and ST Microelectronics that are really high volume facilities. And this slide, which isn't intended to be exhaustive of all of the different foundries, just picks out some different flavors of silicon photonics platforms that are available and some of the foundries where you can access them. Of course, you need more than just the foundry, and this is where the ecosystem is really evolving rapidly over the past decade. There are many software design simulation tools available now. Some of them are open source. And packaging, I'd say there's been very strong progress in that over the past several years. There are pilot lines in Europe. There are research facilities where you can do packaging, and volume facilities such as those provided by Fix in the Netherlands. And wrapping up in the next couple of minutes to give people a chance to ask questions, I've got one slide to give any of those amongst you who are designers some rules of thumb that you can go by and consider during your design. So a sensible tolerance number for any layer thickness or etch is 5%. I've said or plus minus 10 nanometers, like whichever one of those gives you the biggest number. So what I mean by that is if you consider the layer thickness is supposed to be 220 nanometers, in the, say, worst case scenario, it might be 5% thinner or 5% thicker. When we do an etch, likewise, it might be 5% shallower or 5% deeper. And of course, these tolerances accumulate. So if we're doing a lot of steps, you need to consider that a 5% error, for example, on a deposition step, and then if we wanted to do a CMP step to thin it down, we'd have another 5% error. They don't often cancel each other out unless you get lucky. They tend to accumulate and get worse. So like I said at the very beginning, it's very important to consider these during the design phase so that it makes sure that you can build robust devices. Now, when we're talking laterally in terms of feature size dimensions that are defined by lithography process, a sensible rule of thumb is to assume a plus or minus 15 nanometers in all dimensions. So what you can do, if time allows, you can take your ideal device, you can make it 15 nanometers smaller, you can make the etch depth 5% shallower, and you can model the effect of that, because that will then tell you what you may get from a real device. Now, I've made a comment at the bottom that, of course, some fabrication errors or tolerances can be corrected using integrated heaters, but clearly you're limited by the number of pads you can access, and it's not an ideal solution because it does require power to drive those heaters. I've got, I think, 2 or 3 very quick slides just to tell you about what else is going on. We do have 2 live calls. The first one at the top there, MPW38, is our active device call. It's been launched in the last couple of days. If any of the audience are from UK universities using existing EPSRC funding, you do have free access to this MPW run, limited to 1 design area per research group. So please do check out our website if you're interested to have a go at building and testing a modulator. And in the coming days, it's not yet live, we will also launch a new silicon nitride MPW call as well. So please check our website, follow us on LinkedIn to make sure you don't miss that. If you're very intrigued by everything you've heard in the past 45 minutes and would like to see it for yourself, we do offer a chance to do that via what we call an experience centre. It's part of the Photon Hub Europe programme. It's a 3-day hands-on course where you'll gown up, you'll go into the clean room, you'll start with a blank SOI wafer, and by the end of the 3 days, you'll be able to take home a functioning thermo-optic modulator. So if you're interested, please do go to the website that's listed there. The cost will be €2,000 per person. We have limited spaces, so don't miss out. The first date will be sometime in the autumn. Please do follow us on social media. Make sure you don't miss any of our exciting announcements. And thank you very much for your time and attention. I'll stop talking now and let you ask any questions.
Thank you so much, Callum. That was fantastic, really interesting.